Hi, and welcome. On behalf of Intel, we're thrilled to be a sponsor of Eurographics'21. I hope you and your families remain safe wherever you are in the world. My name is Jim Jeffers, and I lead Intel's Advanced Rendering and Visualization team. Soon I'll hand the talk off to Senior Graphics Engineer on my team, Sean McDuffie. Sean and I are here to present the Intel OneAPI Rendering Toolkit and how the libraries contained within can help you deliver high-performance, ray-traced images for your projects. So with a 10,000 meter view, what is it? The OneAPI Rendering Toolkit is a collection of fully open source, multi-platform libraries that each targets a common problem with today's rendering applications, and it builds on the path tracer paradigm. Each of these libraries, starting with the widely adopted Intel Embree library, building out to OpenImage Denoise, the Open Volume Kernel library, and the OSPRay Rendering API brings graphics application developers high performance, high fidelity, flexibility, and scalability across today's CPUs and soon Intel Xe GPUs. The capabilities allow rendering engineers to concentrate on their customers, the needs of the filmmakers and artists, the data scientists and architects, and the designers, knowing the deep level of optimizations on the hardware they are running are taken care of by a fully open, transparent set of libraries. The OneAPI Rendering Toolkit first started over 8 years ago with the Intel Embree library. Now we'll get into more details on that library in a minute, but our team and former team members are thrilled with the recent recognition of Embree's impact by the Academy of Motion Pictures at this year's Scientific and Technical Awards ceremony. So if you're a user or developer using our rendering toolkit, you know you're getting the maximum benefit from years of expert work. I would like to take this opportunity to thank you and all our industry colleagues and partners who helped make Embree such a useful tool from film to scientific visualization to gaming. With that, I'll hand off to Sean to take you on a tour of the Intel OneAPI Rendering Toolkit. Hope you have a great day.
Thank you very much, Jim. Like Jim said, my name's Sean McDuffie. I want to just getting back to the whole OneAPI rendering toolkit. This slide is the one that I really want everybody to walk away with. Why the Intel OneAPI toolkit? And that's simply these 5 bullet points: performance, functionality, flexibility, scalability, and openness. We've done the work to maximize the performance of each library on your hardware. We're fully open source, we take pull requests, and we're very responsive to our customers' needs when it comes to the functionality and feature set of all the offerings in the rendering toolkit. The APIs for each of these libraries is best in class to give you the flexibility to integrate into a wide variety of applications. And as we'll see, our libraries scale from laptops through workstations to render farms to the world's largest supercomputers, from preview renders to final frame beauty passes. These 5 things: performance, functionality, flexibility, scalability, and openness. And one of the things we like to say at Intel with the rendering toolkit is no transistor left behind. That is, we optimize on your hardware so you don't have to. We also say no pixel left behind. That is, we provide world-class visual fidelity for applications that integrate our libraries. And as you see on this slide at the bottom, no developer left behind. Our libraries are not just foundational to the production film industry, but we are deep into scientific visualization, 3D product and architectural design, gaming, and AR and VR applications. Whatever your graphics application is, we want to be a part of helping you succeed, and we want you to be a part of our community. And now here's just some snapshots of that community. Here's an example of the Blender Foundation's integration of Embree and OpenImage Denoise, where they're bringing real production values to Tangent Studios, where they've seen a 5 to 6x speed up in render times after Embree's inclusion, with further decreases due to the denoising power of OpenImage Denoise. Now those speed ups, they're allowing artists faster preview times, more iterations on their shots, hopefully less time in Sweatbox, and more opportunities to innovate on their art while hitting those deadlines and staying on budget. If you'd like to hear more directly, please look up Tangent Studios' Jeff Bell's recent talk on how Intel helps accelerate their rendering workloads. Now here's some more customer stories from Chaos Group. Chaos Group's world-class renders VRay and Corona are built using Embree. Here's a classic example where our close engagement with our customers has driven the functionality that we talked about with our libraries. In responding to our customers' needs for efficient subdivision surface displacements, we achieved a 90% reduction in the memory cost for their meshes, while matching the visual fidelity needed for them to service their customers across the film industry. And I just love this slide. It's great to see our work in helping a customer who then has their own customers. Here, that's filmmakers. And then once again, they have their customers, the audience. And I think the open source nature of these libraries has a big part to play in driving that. If you'd like to see more, please look up Chaos Group's Phil Miller sharing how Intel OneAPI Toolkit was a big win for them. So now let's move on from that overview picture and let's start diving down into each of these libraries. We're going to talk about Embree, then we're going to talk about OpenImage Denoise, Open Volume Kernel Library, or OpenVKL as we often say, and OSPRay. So we're going to start with Embree. So what is Embree? All right, so Embree is a highly optimized ray tracing kernel library. What that means is that Embree provides routines for high performance ray surface intersection queries, which is the foundation of ray tracing applications. These kernels are optimized for the latest CPUs with support for SSE, AVX, AVX2, all the way to AVX512, along with a runtime selection mechanism to choose the intersection code that best matches the instruction set that's available to you on your hardware. Embree is available on all major OS platforms, Windows, Mac OS X and up, Linux, and is available open source under the Apache 2.0 license. Embree contains algorithms optimized for both incoherent workloads, they're the majority of workloads in path traced scenes, and coherent workloads, such as primary visibility rays and hard shadow rays. The API allows for easy integration into current rendering applications, along with the flexibility to extend the ray intersection calls to unique geometry. The API also supports queries for single rays, ray packets, and ray streams. Both closest hit and occlusion only queries are also supported, along with user-defined ray filter functions which can be run on hit with user data. And it has developed a uniquely robust feature set right out of the box. Key advanced features needed for production rendering include hair, and fur, and complex line geometries. We also have efficient subdivision surfaces with displacement, multi-segment and quaternion motion blur, multi-level instancing, that is nested instances in instances, and as I said, the flexibility of user-specified geometries, along with many more which you can see on our webpage at www.embree.org, where you find a number of tutorials covering all the advanced features we support, such as closest point queries, vertex data interpolation, point geometries, and more. With Embree, you really are getting best-in-class performance and a library that's continuously evolving to maintain the performance advantage and feature set needed by rendering application engineers. This is why Embree has been so widely adopted and recognized across the film industry, because it reduces render times, freeing that computation, freeing those developer resources for more complex scenes, pushing that problem space out, and raising the bar for higher visual fidelity across the industry. And here on this slide is just a taste of the number of applications and companies which have integrated Embree into their software, from in-house renderers at DreamWorks and Illumination, commercial applications like VRay and Corona, to open source creation suites like Blender. And as we move forward into the future, know that we are looking to add direct ARM support, and with Embree 4.0, really a major initiative across the whole OneAPI rendering toolkit is going to be our XPU support, leveraging all the compute available from today's Xeons through our future Xe GPUs, while also leveraging Intel's Optane persistent memory. The pitch line here is, as Intel hardware is going to grow into the future, so will Embree. So let's talk about the next library we want to showcase today, OpenImage Denoise. All right, so let's go back to that question, that why question again, and really why Monte Carlo path tracing? And the answer to that question is Monte Carlo path tracing is able to capture the wide variety of effects of light transport that other rendering algorithms typically end up becoming overburdened by. Now, each pixel is taking a random sample of the scene, and over the course of many samples per pixel, we converge to an accurate image. And getting pretty close, it happens pretty fast, but full convergence unfortunately can be quite slow, resulting in noisy looking images. Fully converged final frame production quality renders can often take hours or even days of CPU time based on today's hardware, which is detrimental to the artistic process and the business of filmmaking. So enter denoising algorithms. The question then becomes, can we get something as good as this ground truth image here, done with 32,000 samples per pixel on a much smaller budget? That is, can we do it with orders of magnitude less samples? Here is the raw image with only 16 samples per pixel next to ground truth. And the answer is yes. With Intel's Open Image Denoise, we can efficiently get much, much better estimates of the final resulting image in a fraction of the rendering time needed for a fully converged image. And when used on higher sample counts, say around 1,000 samples per pixel, we can get results that are indistinguishable by the human eye from ground truth at still a fraction of the time. So here is the overview slide for OpenImage Denoise. What it is an AI-based denoiser that focuses on high-quality denoising for multiple applications, suitable for preview, for final frame, for baked light map denoising. And like with Embree and all the libraries in the OneAPI Rendering Toolkit, it is available on Windows, Mac OS, and Linux under the open source Apache 2.0 license. And we will note here, OpenImage Denoise is multi-platform. We support x86 and Apple M1 CPUs. How can you leverage the power of OpenImage Denoise? We supply a pre-trained neural network that can take as input multiple image buffers that typically are available by today's renderers, such as the original noisy color image, along with optional albedo and normal passes to output a high-quality, noise-free image close to ground truth. And I really want to emphasize how little work this takes. The AI-based denoiser is a huge step from previous denoising strategies that required extensive setup and tweaking of filter parameters. Here, the AI solves that parameter space for you. Also, while we ship with a pre-trained neural network, you are also free to train your own network on your own data. Once again, the focus here is on performance, functionality, flexibility, scalability, and openness. Touching a bit more on that functionality, as mentioned, we can take in multiple input buffers. We support denoising of low dynamic range images as well as high dynamic range images. High intensity fireflies are not clamped, which would lead to a darkening of the image when compared to ground truth. Instead, that energy is distributed smoothly across the image, avoiding the typical blotchy denoising artifacts that are common in others. And like I said, you are free to train your own network, specialized to your projects. So let's take a look at some more examples. Here we have an interior scene using the Corona renderer, which was sampled with 16 samples per pixel. And as expected, the low sample count is resulting in a lot of noise, particularly in the areas mainly lit with secondary light. Applying OpenImage Denoise, we are able to remove this noise and get a clean image, which is quite close to that ground truth, which here requires 64 times the number of samples per pixel to achieve. And OpenImage Denoise is not limited to denoising images rendered from a camera. We also support denoising light maps, which are heavily used in games to mimic global illumination using textures. Here we see even medium sample counts of 512 samples per pixel are still quite noisy, which in the final render would result in blotchy artifacts in the game world. With OpenImage Denoise, we are able to efficiently remove this noise completely at a fraction of the cost otherwise. And here's an example of what those blotchy artifacts can look like. Notice the secondary lighting near the beams towards the top of the image and elsewhere in the room, sides of the couches. And now after a quick pass with OpenImage Denoise, this is good for final rendering. And once again, a side-by-side comparison. Like Embree, OpenImage Denoise has quickly found itself in many rendering applications, and if you are working in the 3D content creation, product design, or VFX space, you can easily enable OpenImage Denoise on your own images. So we encourage you to engage with this open source community and see how it can speed up your workflows. Moving into the future again, we are working on several improvements. One feature will be part of the next release is a better handling of noisy albedo and normal feature buffers. By applying an additional pre-processing step to denoise these features, we are able to further improve the quality and sharpness in textured regions. The latter is especially important for denoising animations and to avoid flickering at lower and medium sample counts. And like Embree and the rest of the OneAPI rendering toolkit, we are moving to support Intel's XPU future, including discrete Xe GPUs. So let's turn our attention to one of the newer libraries, the Open Volume Kernel Library, or OpenVKL. Now, OpenVKL is similar to Embree in that it offers a high-performance library for ray sampling of scene content. But where Embree concentrates on computing surface samples, VKL covers the domain of volume sampling and, in addition, efficient traversal of array through volumes. And we have the same story we've seen previously. We have full support for the latest CPUs and CPU instruction set architectures, including AVX512. That is, we have performance covered for you. We are available on all major OSs, and we provide a flexible API for easily enabling VKL integration into existing applications. And once again, we're fully open source under that Apache 2.0 license. And OpenVKL is a uniquely feature-rich volume traversal library. Like Embree's flexibility with multiple surface data types, tri-meshes, curves, subds, etc., we have multiple volume data types available out of the box, each optimized for the hardware platform you're running, giving you the flexibility to match your compute and memory demands to your problem. We have structured volumes, which are dense regular voxel grids, very fast, highly optimized data structures for small to mid-size volume data sets, a VDB-like or sparse structured regular grid data structure, which the VFX and animation world is acutely familiar with, and which we're going to cover a little bit more in a second. And then other volume types which haven't seen as much use in the film industry but are heavily used in high performance computing, such as supercomputing physics simulations, such as spherically structured data for problems that are inherently spherical, adaptive mesh refinement based volumes, or AMRs, which allow for extreme precision where one needs it but sparse data where you don't, along with fully unstructured data that can exactly match any data set. And in addition to these cell-based volume data structures, we also support direct traversal of particle data sets defined with radial basis functions from, say, for example, smooth particle hydrodynamic simulations. Now, along with these volume data types, we also provide a powerful API for solving common ray volume traversal problems, such as sampling the volume and computing gradients at the sample locations. We also provide ray-based interval iterators and support computation of implicit isosurfaces. And we give developers flexible and custom access to volume traversal data through volume observers. And these APIs are agnostic to the volume type. You can write your renderer with the VKL sampling API knowing that the special optimizations handling of different volume data representations is going to be taken care of for you. And now just swinging back to our OpenVDB support with OpenVKL sparse grids, we supply an internal representation based on VDB, which allows very fast access of data while efficiently using the memory available to the renderer or other application. And you can load and sample your VDB files directly. Diving in on some more of those features that are important for VFX developers and artists, OpenVKL now offers direct support for motion blur, though this is currently only for our dense grid volume type. OpenVKL's API gives users the flexibility to match their temporal data to their needs. We offer a very fast, high-performance, structured temporal data representation, that is, same number of time steps per voxel. And we also offer the flexibility and memory savings of fully unstructured temporal data, commonly referred to as TUVs. That is an arbitrary number of time samples per voxel. Here, once again, you're seeing functionality coupled with performance and flexibility. And continuing with that story of functionality and flexibility, as mentioned earlier, the OpenVKL API offers ray-based interval iterators. This allows applications to iterate over meaningful intervals of their data. Here in this image, you can see the intervals of a ray highlighted in yellow. The library offers different data over those intervals for the varying needs of today's renderers. For example, value rangers per interval for delta tracking based integrators, and also step size information per interval for ray marching based integrators. And here are just going to be a couple more examples of renders from our Cloudscape demo at SIGGRAPH last year, which was rendered with OSPRay, which we're going to cover in a sec. I just always like this image. It really gets back to another one of our core takeaways for this talk, scalability and a dedication to visual fidelity that you get with the OneAPI Rendering Toolkit. Once again, we're going to look into the future. OpenVKL is rapidly moving towards its 1.0 release, and a major extension is in the works to add motion blur sampling support to our VDB volumes, so stay tuned. Also, like the rest of the rendering toolkit, we will be moving towards that full XPU support to cover all the compute available to you from those Xeon CPUs to those future Xe GPUs. And now, we just saw some of those images rendered with the path tracer that ships with OSPRay, so let's dive into OSPRay fully. So OSPRay is our open source rendering framework which builds upon each of the previously presented lower level libraries. OSPRay itself is really an API for writing renderers, which offers a set of ray tracing algorithms with which one can write different rendering applications, ranging from scientific visualization to photorealistic images generated with path tracers. And the library ships with both a sci-viz focused renderer and a path tracer. A key part of the OSPRay story is that it scales. It doesn't just run well on a local laptop CPU, but it can also efficiently operate on the largest multi-node supercomputers in the world. OSPRay is able to handle massive amounts of data, which can quickly grow to many, many terabytes in distributed environments, all while being available on all OSs and still being fully open source under that Apache 2.0 license. And because of the scalability and openness, OSPRay has become a key renderer in the world of high-performance computing for visualizing enormous data sets. Here's one such example, a collaboration with the Stephen Hawking Center for Theoretical Cosmology at Cambridge University. This is a simulation of two black holes spiraling into one another, and we are visualizing the creation of gravitational waves over the course of a multi-frame animation. We're talking about a 36 terabyte simulation being visualized at interactive frame rates of 10 frames per second on a workstation scale system. This power is why OSPRay is being used by many research institutes all over the world, and is incorporated into Kitware's highly successful ParaView toolkit. But we don't just have a sci-viz focused feature set. As I said in the intro, we also ship with a photorealistic physically based path tracer. OSPRay includes physically accurate lights and physically based materials. And the OneAPI Rendering Toolkit comes with two applications built on this OSPRay rendering framework. The first of which is shown here, Hydra for OSPRay. That's a USD Hydra delegate for OSPRay, allowing USD-based scenes to be rendered directly with OSPRay. Hydra for OSPRay supports two modes, a fast preview mode and a final frame beauty pass mode. And it supports a variety of different USD features such as USD Lux light source, full translation from the USD preview surface to OSPRay materials, PTEX textures, instancing, and many, many more. And like everything shown today, fully open source under Apache 2. Here's an example of the USD version of the cover scene from Farr et al.'s PBR book being pushed through Hydra for OSPRay. And we also have OSPRay Studio, which is an extensible asset viewer and look dev tool. Studio can be used to load and view assets from multiple file formats such as OBJ, GLTF, BDB, raw volume data for use with OpenVKL. And the UI provides basic functionality for building a scene and setting up materials,
We use it regularly for our own tech demos at SIGGRAPH and other conferences, and it's available out in the open, as is all the code that we offer. And it's not just us using it either. Bentley Motors Limited has been using OSPRay Studio to render their virtual car models with photorealistic quality and materials at interactive frame rates. In here, we have everything coming together. I love this picture too. The Moana Island scene with the Disney cloud, all rendered in OSPRay. We're using Embree for surface intersections, OpenVKL for volume traversal. The whole image was denoised with OpenImage Denoise, and this was run on scalable hardware with OSPRay.
Great job, Sean. Thanks for that detailed overview of the InteloneAPI Rendering Toolkit components and our upcoming features. Well, that's all the time we have for today. I'll leave you with a quick recap slide. We'd love you to visit the Rendering Toolkit URL and take a deeper dive. Also, you can follow me on Twitter at James L. Jeffers. Thanks and have a great day.